Hey guys, welcome back. I'm going to do the rest of the notes for those of you who aren't going to be in class today. So this is the second part of the circular motion notes. We left off with the car turning and a free body diagram that has been drawn with the friction going towards our center, weight going down, normal going up. We have already solved for the centripetal acceleration. All right, so it asks for what our force of friction is. So friction in our picture is our centripetal force in this case. So I'm going to have F net equals mv squared over r. I'm going to take the forces towards the center minus away. In this case, there is nothing away, which we don't have to have something away, but we have to have something towards. So that means that it's just going to be that friction is equal to mv squared over r. So our friction is going to be equal to our mass, which is 1,200 kilograms. We already figured out what our v squared over r was, which was 4.2, or 4.16. So I can just plug that in as my v squared over r. All right, so this is giving me 5,040. All right, now the question is, what does the minimum coefficient have to be? Because friction's only as much as it has to be when it's static friction. This is static friction, it's not slipping. So in that case, I need to look at the normal because I know that the static friction is less than or equal to mu n. And let me switch colors so it's a little bit more apparent. So in the y direction, we have balanced forces. We have F net equals 0. So when I take my ups minus my downs, I'm going to get that the normal is equal to the weight. So that's going to tell me that the normal is 12,000, which is going to be 1,200 times 10. And so my mu at least has to be equal to how much friction I need divided by the normal. So this is going to be 5,040 divided by 12,000. Again, mu is unitless. So we have 0.42. All right, the next question in the notes is just a quick review so we can do the pre-lab today, so we can do the lab tomorrow. All right, so a rubber stopper with a mass of 25 grams is rolled around in a horizontal circle with a radius of 0.7 meters at a constant speed. So this is going to be similar to what you guys are doing in the lab. Now in the pre-lab, there's an example where we have a vertical circle. This would be a vertical circle. What we're looking at is a horizontal circle. So you're going to be trying to whirl around your head without hitting yourself in the head. Completely horizontal, just fast enough to support different masses. All right, so is the circular motion uniform? Yes. Why? Because it's at a constant speed. So uniform circular motion is one that's happening at a constant speed. This is useful to us because then we can just use our F net equals mv squared over r, and not F net equals ma as well. What is the distance the stopper travels in one revolution? Well, the distance around a circle is a special distance, which is 2 pi r. So my radius is 0.75 meters, and it looks like this is going to be 1.5 pi meters, which is 4.7 meters. What is the period of the rubber stopper? Now, when you time this, or your partner times it while you whirl, we're not going to time it one time around. You're going to time it for 10 revolutions. You're going to time it for 10 revolutions, 10 different times. Why wouldn't we do one revolution? Well, our error, just by hand timing, is between 1/10 and 2/10 of a second. So if we're going around and it's only going to end up being 0.35 seconds, you're adding a huge amount of error in there. But if we time it for 10 and then divide it by 10, we can get what 1 is a lot more accurately. So 10 revolutions takes 3.5 seconds. So if I divide this by 10, I get that 1 revolution is going to take 0.35. Now we have to be careful that we divide that by 10, and then we have to average 2 because it'll mess up our speed. All right, so the speed of the rubber stopper. So if we're in uniform circular motion, we have a special formula for this speed. And this is our special distance over our special time. And our special time is the period, and we designate that as a capital T. So capital T is our special period. So this is going to be our 2 pi times 0.75 meters divided by 0.35 seconds. And this should be 13.5 meters per second. The other thing that we're going to have is you guys are going to be spinning a rubber stopper around your head. In the video we looked at Julius Thunder Miller, he was spinning a mass around his head and he hit himself in the head with a mass. A rubber stopper is going to hurt a little bit less if you actually end up hitting yourself with it. So we need to convert. So I know that it's 25 grams. I want to go to kilograms, so that's going to go up here. This prefix K is 10 to the third. So I'm going to have 25 grams divided by 1,000. And so this is going to be 0.025 kilograms. All right, so what's happening is that we're spinning this around. If I were to draw what this is looking like, I have my rubber stopper, and I have my string. On my free body diagram, I would have weight going down and tension going towards the center. And that's it. That's our free body diagram for us. For our lab, we're going to have a glass tube that the string goes down. And the glass tube is smooth, so it makes it like a frictionless surface. And we're going to hang a mass from the bottom that we're going to suspend. So we have an F net equals 0 down here, and we have an F net equals mv squared over r up there. So the centripetal force necessary is this mv squared over r. So this mass is what we're whirling around, what is going in a circular motion. And that mass is the rubber stopper. So I'm going to take the rubber stopper's mass, and that is 0.025 kilograms. The speed that we solved for, which we said was 13.5 meters per second, that's squared divided by 0.75. And this ends up being 6.1 newtons. So this is going to be our centripetal force. And for us, this is going to be our tension. When you guys do the lab, I think that our velocities are around 7 or 8 meters per second. But it's going to vary because we're going to be changing the mass that we're suspending.